Pronto, João. Quando você quiser começar, eu já estou pronto aqui.
Okay. So, hello everybody. I'm João Rodrigues, Brazilian guy. It's a pleasure to present now Professor Roberto Dovesi. Professor, just a few words about Professor Dovesi. He has his PhD in theoretical chemistry at the University of Torino in Italy. Mainly, Dovesi has important works in quantum mechanic approach to solid state chemistry, physics, material science, and surface science. Mainly, he worked with implementation of Campina computer programs, to study electronic and periodic compounds. In particular, I found his work mainly because I would also work with this kind of things, simulations of DFT to predict the vibrational properties of materials. Mainly, this is my work. In the main outcome of his achievements, the program called Crystal. Now he is full professor in head of theoretical chemistry group of the University of Torino. So for me, it's a pleasure to present Professor Dovesi to this nice talk, entitled Vibrational Frequency in Solids, Tools and Tricks. Now it's up to you, Professor Dovesi, to start the seminar.
Okay, thank you very much for the invitation in those difficult days. I will try to be clear if I can, and to go slowly, but obviously if something is not clear, so you can stop me or ask question at the end. So the subject are vibrational frequency in solids, and the idea is how can we learn about the properties of solids looking at these spectra that are generated by the vibrational part of the mechanics. You know that there is an important approximation that is called the harmonic approximation, according to which when we have, say, a biatomic molecule and we change the distance between the two atoms, the potential energy is parabolic. Actually, this is not parabolic, we know, because the curve is much more repulsive when we compress and tends to be flat when we pull the two sides. But the harmonic approximation is essentially a necessary tool if you want to study relatively complex objects, and it is not bad in many cases because anharmonic effects are relatively small, apart from special cases that maybe we will discuss later on. So the harmonic approximation essentially is a way to decouple the equations of motion of many particles, because through a transformation of the space, we go from the Cartesian coordinates of all the atoms in the molecule or in the solids that are moving in a collective way to something that is called a normal mode, or a set of normal modes, according to which those movements are independent. The usual tricks the usual tricks in physics, in chemistry, everywhere, to separate variables is to diagonalize a matrix so that the matrix after diagonalization is diagonal and mixed terms disappear. Okay, so when we look at a molecule, we know that if there are n atoms, there are 3n minus 5 vibrational modes if the molecule is linear, and 3n minus 6 in the other cases if the molecule is not linear. And 6 means that there are 3 translations, so a molecule, the degrees of freedom of the molecules contain 3 translations, so 3 coordinates can be used for describing the translation and 3 for describing the rotation. What is left, that is 3n minus 6, if the molecule is not linear, are the inner displacement of one atom with respect to the other, and then are the vibrational modes. Obviously, to go from the Cartesian coordinates to the coordinates describing the translation, the rotation, and the vibration, one must do similarity transformations of the coordinate space. So, for example, if we look at a molecule, say water, with 3 atoms, and then 3 atoms, there are 9 Cartesian coordinates, but 3n minus 6 is just 3, so the water molecules has just 3 vibrational modes, and they are well known, and they are the stretching, the symmetric stretching, the symmetric antisymmetric stretching, and the bending of the molecule after the analysis. But from the point of view of the knowledge, obviously the molecules as they are microscopic objects, so we cannot see them. And the way we know what happens at this level is through experiments. And so the question is, are all those vibrational modes, 3 for the water molecule, visible in experiment? And then the second question is, can we simulate those modes? Well, there are, as for many experimental techniques, there are selection rules. That is to say, not all the vibrational modes of a molecule, and then we will see of a solid, is visible in when we perform an experiment, because the probability of the transition from the ground state of the oscillator to the excited states is forbidden. This is strongly related to symmetry. So the modes can be classified as active or silent. And those selection rules that are well known since a long time, but are different according to the kind of experiment, because those selection rules are matrix elements between the ground state, a given operator described in the interaction of the electromagnetic field with our molecule or solid, and the final state. So, for example, if we use the two by far most popular techniques for investigating the vibrations of molecules, the infrared and the Raman, the selection rules are different because the operator is different, and then the infrared or Raman spectrum of a given molecule can be quite different. For example, if we consider methane, methane is CH4, so there are 5 atoms. 5 atoms means 15 coordinates, minus 6, there are 9 modes, 9 peaks that can be expected in the spectrum. But the situation is quite different because for various reasons. First of all, many of the eigenvalues, if you want, the energies are degenerate. So there are only 4 peaks because we have degeneracy of 3, 2, and 3 for many of those peaks. So 3 plus 2 plus 1 plus 3 is equal to 9, is the 9 what we are expecting. But if 2 modes are degenerate, obviously in the spectrum they appear at the same energy. And then there are the selection rules, so that, for example, when we do a scanning, you know that in ER or Raman spectroscopy, the units is centimeters to the -1. Usually used, that it can be considered the energy of the wavelength, but usually is used the centimeters to the -1. Then the 4 modes have different symmetry. F means 3-fold degenerate, E means 2-fold degenerate, so that in infrared there are just 2 peaks, whereas in Raman there are 4 peaks. So 2 peaks active in infrared and 4 peaks in Raman. So the 2 spectra are quite different because you see, if this is the intensity, it is clear that this one will disappear completely. 3 with respect to 1000 will disappear completely in the spectrum. So the spectrum will be completely dominated by those 2 peaks, whereas this one and this one are roughly the same in the infrared spectrum. So it is clear that different information can be obtained performing different experiments. And there are many other features because we can play with light, and we can have depolarized light that might add additional variables I'm not going to enter here. Obviously there are other obvious considerations. For example, it is clear that a mode can be forbidden, but maybe it is allowed, but the intensity can be in some cases so low that you cannot see. But another features that makes the interpretation of the experimental spectra difficult is that by chance you can have peaks that are very close to each other, and then what you see in the experimental spectrum, you have a big peak that actually is the superposition of 2, 3, or many peaks, so that the deconvolution of this spectrum is not simple. Then, obviously, with respect to the analysis that I will try to do, using the harmonic approximation, we must anyway take into account that the vibrations are anharmonic. And then in the discussion, in the literature, very often we find the word forbidden peaks that appear, because those peaks are forbidden if one remains in the harmonic approximation. They are not forbidden if one takes into account anharmonicity. But usually, in many cases, anharmonicity is a very small correction with respect to harmonicity, so that those peaks are very often very small peaks. So in general, frequently you can have a spectrum with big peaks and then very small peaks, and those small peaks can be can inform you that there is a contribution from anharmonicity, But obviously, those can come from impurities, background, temperature effect, isotopic mixing, because you know that the harmonic oscillation that you study in the first or second year, obviously the frequency of the oscillation depends on the inverse of the square root of the mass. And when you have a mixing of various isotopes, for example, in carbon, you know that you have a small percentage of C13, not only C12, but C13, and obviously the mass is slightly different. So very often, if your experiment is very precise, you can see the main peak due to C12, but also a small peak due to the proportional to the percentage of C13, it is around 1%. Okay. Well, so when we are looking at an experimental spectrum, it's difficult to, at first, to know exactly what we are looking at, because it is not clear how many atoms there are in our system, in a solid, and it can happen that many of those modes are non-active, or they have a very low intensity. So the help, the synergic use of the simulation with experiment is extremely useful, because with simulation we build your system, you know which atoms we are introducing, and using quantum mechanics and using group theory, you can know a priori how many peaks you should have in your spectrum, and then you are in a position to compare your simulated spectrum with the experimental one. But most of the comments were referring to molecules. But what happens when we go to solids? Obviously, solids contain a new, you know that the model that we are using for solid is that the solid is infinite. Actually, all solids are finite, but the model that is always used is to consider the solid as infinite, because, for two reasons. Because if we build a model that is finite, then we should take into account the fact that periodicity is lost, and that would be a disaster. But the reason that permits us to think the solid is going to infinity, so we take, you know, a unit cell and we repeat to infinity, is because in the bulk properties are not perturbed by the surface properties if we look properly at the bulk properties, in the sense that the number of atoms in a relatively macroscopic object, the number of atoms in the bulk is orders of magnitude larger than the number of atoms on the surface. So, for example, when we define a simple any property of bulk, we don't have to care about the shape and size of the macroscopic object we are considering. So if we say that the CV of iron is 7, say, this is independent on the from the size and shape of the object that has been measured. So when we look at solids, in principle, we could look as a molecule with an infinite number of atoms. But if the number of atoms is infinite, then we have an infinite number of degrees of freedom. And then when we do the dynamics, we should build infinite matrices, and those infinite matrices obviously cannot be tripled. You should multiply infinite matrices, diagonalize infinite matrices, invert infinite matrices. But the very good point for crystalline solids, not disordered solids, crystalline solids, is that we have the translational symmetry. Translational symmetry permits to organize the infinite number of objects in a finite set. You know that for solids, we consider the unit cell. So for example, in bulk MgO, we can concentrate our attention on two atoms, one magnesium, one oxygen, that obviously are repeated an infinite number of times, but essentially this permits to come back from infinite to finite, and for many properties, the number of quantities of interest actually is proportional to the two atoms. So, for example, for the vibrational spectrum, infrared and Raman spectrum of MgO, we can limit the attention to 6 coordinates, 3 for magnesium and 3 for oxygen. Although then the infinite character reappear because the dynamical matrix that must be diagonalized for obtaining the vibrational modes is not just one. There is one that is at the center. I hope you are familiar with the Brillouin zone. Now, the Brillouin zone is a dual space with respect to direct space, in which the infinite nature of the crystal is reflected to give an infinite number of K points. In a sense, the Brillouin zone is an extremely powerful result of the exploitation of the translational symmetry. The translational group is a very important group that contains an infinite number of operators. Actually, we have infinite to the cube because we can translate along, say, A, then along B, along C, so that at the end, to be short, for example, if we compare the situation of a molecule, say the MgO molecule, an MgO solid, in a sense, in one case, in the other, we should expect 6 coordinates for the vibrational spectrum, although then the solid will present what is called the dispersion in reciprocal space, so that there are actually 6 eigenvalues, not only at the center of the first Brillouin zone, but for each K point of the Brillouin zone. So is this relatively complicated point important or not? For example, if you are interested in the infrared or Raman spectrum, no. So if we do the infrared spectrum and the Raman spectrum of MgO solid, actually we must build a matrix that is 6 by 6, 3 coordinates for magnesium, and diagonalize this matrix. Okay, so the situation is simpler. But if, on the contrary, we would like to investigate the thermodynamic properties of MgO, so for example, how temperature can augment the volume of MgO, then in this case, we could take into account not only the gamma point, but all the K points. There is one more point delicate that should be discussed, that I just mentioned, is that the infinite number of K points in the Brillouin zone actually are the properties, for example, the eigenvalues, the eigenvectors at each point are similar to the nearest points, so that it's not necessary to know the eigenvalues, the eigenvectors, or the dynamical matrix in all points, but it's sufficient to have a set of k points and then interpolate among those points. Okay. So this is what I was saying. For the R and Raman spectra, it is sufficient to know what happens at the gamma point, that is the center of the first periodic form. For the thermodynamic analysis, we must have much more expensive calculations, because we must know all the eigenvalues for all the k points. Okay, this is roughly what I told. A given point in reciprocal space is represented as a k point, and the other important information concerning vibration is that the number. You remember that in a molecule, for example, in methane, there are 5 atoms, 15 coordinates, and 3 of those coordinates must be separated for the translation and 3 for the rotation. In a solid, we could do the analysis, but the number of vibrational modes is 3n minus 3, because we must take into account the translation, the possible translation of the solid, but not the rotation of the solid. I will not enter into this part of the discussion, but okay. So how we are computed the vibrational modes in a quantum mechanical code, in the case of crystal, what we implemented. You see that this light is very old, comes from a crystal school that we did in Brazil 6 years ago. And so the point is to build the matrix that contains the second derivative of the energy with respect to the coordinates of the atoms. And in crystal, as in many other periodic codes, this is done semi-analytically. Semi-analytically means that the first derivative is analytical and the second derivative is numerical. So this is just a technical point. But then the harmonic frequencies are obtained diagonalizing this W matrix. And this W matrix is the one that contains the second derivatives, but it contains the masses to the denominator, you see. Like if you remember the formula for the harmonic oscillator, the masses are to the denominator. And this is quite important because changing the masses is one of the tools we will see that can be used for analyzing the spectrum. You know, for example, if you have 20 peaks in your infrared spectrum of your molecules, one of the question is always which atom is some of the atoms contributing in particular to one peak or not. So if we change the mass here to the denominator, we can see how the spectrum is changing when, for example, the atom number 3 is attributed to a different mass. And this is quite useful, as we will see. Well, then in solids, things are slightly more complicated than for molecules, because the spectra, there are two kind of modes. The one that are called the transverse optical modes, that are, say, similar to the ones that we have in molecules, so you want to, and then the longitudinal modes that are parallel to the wave propagation. So in general, the the shift between the TO and the alone is not big, but it's there and can be analyzed and can be understood. The simulation can generate both set of eigenvalues. I will not enter here into details because time is running. Obviously, there are technical aspects, but this kind of calculations are not extremely difficult. Let me just mention one features that is quite important. In solid state chemistry or physics, there is a quantity that is called the atomic Born tensor, and that is crucial for for three important properties that can be generated by quantum mechanical calculation. This atomic Born tensor is roughly the derivative of the dipole moment with respect to the atomic coordinates. So it's not the dipole moment, it's the derivative of the dipole moment. And it is the main ingredient for evaluating the infrared intensity, because, you know, when we do a spectrum, we have the frequencies of the wave numbers, but also the intensity that are important. But the same quantity enter in the definition of the longitudinal optical mode, and also for the definition of the static dielectric tensor. I will go through quickly because here are technical aspects, but this Born charge tensor is a crucial quantity for those quantities, static dielectric tensor. Okay. Now, how happens? How appears the spectrum from the experimental point of view? In many experiments, what is registered is the reflectivity, and the reflectivity is this quantity that I'm not entering into details, but essentially those are just angles that measure the beam incident angle, whereas epsilon is the dielectric function obtained as the superposition of damped harmonic oscillators. So what is measured, that is quantity, is the result of the fact that in our solid we have many oscillators damped. You see the E is the imaginary unit. And so, for example, this is this one here is the three are three reflectivity spectra, all three compounds, garnet, pyrope, pyrope, grossular, and almandine. They belong to the same family of garnets. But you see that how appears the experimental spectrum that is the one that must provide information on the vibration of our solid. And the dotted line is, the dotted curve is the experimental, and the continuous one is the calculation. And it is from this kind of curve that we must, through the convolutions, obtain the information concerning the spectrum, the wave numbers of the oscillation of the solid that usually are then tabulated, frequency, intensity, okay? And then the problem of the comparison between experiment and simulation is related to the model. What is the model that is used? And actually, what happens when an experimentalist generates this kind of curve, then he must fit with a given model that in many cases is already included in the experimental setup for providing frequencies and intensities. But this is not an easy task. Consider, for example, the systems that we are going to discuss a bit are garnets. Garnets are doing the symmetry and the space group analysis. We know that garnets must contain 17 peaks for infrared. But then the damped harmonic oscillator that we were discussing here contains 3 parameters. Okay, so 3 parameters: Fj, gamma j, and nu j. So if we have 17 peaks and 3 parameters, we must perform a best fit of this curve with a model containing 51 parameters. You can imagine that the fit performed in those conditions provides parameters that are enormously correlated. What I mean is that when you have a simple curve, you know, for example, if you have a parabola and you have a model with 5 parameters, all those parameters can be changed in any way because you have a redundant number of parameters with respect to the complexity of the curve. And it is for this reason that the simulation is quite important, because it helps and start from the other side of the problem. Here you see the formula for those garnets, and those garnets contain, you know, silicon oxygen tetrahedra and 2 metals, a divalent and a trivalent, and according to X and Y, you can have different garnets. They are cubic, and there are 80 atoms in the primitive cell, so that overall we have 240 Cartesian coordinates and then 240 modes, 3 of which are the translation, so should be 237. But when we look at the modes that are active infrared or Raman, we discover that only 17 are active in infrared and only 25 are active in Raman. Then you see that when the symmetry of the object is very high, the selection rule are killing most of the modes, and the spectrum is expected to be relatively simple. This is the structure, you know, they are cubic, there are the tetrahedra of silicon, the octahedra of aluminum or the other trivalent, and then the other is filling the space, in this case in pyrope is magnesium. Okay. And quantum mechanical simulation codes, in particular the crystal code, you know, in a very simple way, can perform the calculation, produce an output that labels, for example, the modes, then provides the wave numbers of the frequencies, the symmetry. This is generated automatically. The symmetry of the mode, if it tells you if it is active or inactive in infrared, what is the intensity, also if it is active or inactive in Raman, and there is another part of the output that gives the Raman intensities. Well, for example, in our coding crystal, to generate the vibrational frequencies, there is just a single keyword, FREC-calc. Once, obviously, the equilibrium geometry has been determined. So when you perform a quantum mechanical calculation, there is a first step for the determination of the equilibrium geometry. And at this point, when you are at equilibrium, you can perform the frequency calculation with a single keyword. So I think obviously that I have, say, 10 more minutes. Elias. Okay.
14 minutes, yeah. 14 minutes, yeah.
40 minutes, okay. So what is the aim of the simulation? Well, there are various, obviously one should convince the reader or who is following here that the numbers that are generated are reliable. We have no time to discuss this, but they are quite reliable in terms of, in particular in relative terms. We'll simply see some examples. And then I will skip essentially the first 2 points. The third one is, can we interpret the spectrum and attribute the modes? Because this is often is one of the questions. Who is moving? This peak corresponds to what? So I will skip all the discussion of the numerical stuff, but we can, so those are cost, also the cost that, okay, so here we have a first example of the vibrational modes for SPES13, that is one of the members of the Garnet family, where you can have a feeling of the how this calculated and experimental wave numbers in centimeters to the -1 compare, or you can have a look to this column that gives you the difference. So when the color is more intense, means that there is a difference. For example, here 640 to be compared with 630. So 10 to the -1 is a relatively big difference. We can say that you know, the excursion is from 100 to 1000. So if the difference between the simulation and the experiment is of the order of, here the maximum is 10, it's not too bad, I would say. And here in the first one was TO, here is LO, you see again. And then we can also compare the intensity. The oscillator strength is the intensity of the peak. So we are interested to see where is the peak, and then how large is the peak, the intensity. And we can repeat the same thing for the Raman spectrum. And you see that in some cases, the difference is a bit larger, or in other cases, you see, again, the difference is so big that certainly there is something wrong with the experiment, because the calculation we could discuss, we have no time, but we could discuss how accurate are the calculations, but there is no reason that one mode is well reproduced and one is completely wrong in the simulation, because all the modes, all the eigenvalues are generated from the same diagonalization. Whereas in the experiment, there are regions that are not easily accessible and other that are more easily accessible, and you must have impurities and things like that. So for example, this is a clear indication that in this experiment there was something strange. You see, let me just summarize what we had here. So we studied 6 systems, and for each of them, 89 plus 89 TO and 89 LO modes have been generated. So about 200 modes. You see the statistics, the mean difference, delta, is of the order of 5 centimeters to the -1, and the maximum is 23. So actually the simulation can generate very accurate infrared and Raman spectra, and for the comparison, for the analysis of the system or for comparison with experiments. And here we see some example of the spectra. You see that the 2 curves, one is the experimental, the other is the calculation. There are cases you see in which, for example, here you see we have just the red one, that is the experimental, whereas the calculated is here. But here is a problem related to the orientation of the sample in the experiments, because we have no time to enter. But, okay, and you know, very often the experimental spectra are not simple. You see something like that, and to have the calculated counterpart can help a lot. You see here another system and the comparison. Again, another mineral. Again, another mineral. Here is, for example, one of the most common defects in diamond. It's called the B center. In this case, the situation can be more difficult because you see the red one is the experimental spectrum, the black one is the simulated spectrum. But you see that here the peaks are not separated; they are all packed together. So the interpretation requires a long discussion. But one of the points that should be underlined with respect to defects is that when you do an experiment, say on looking for defects, say in diamond, you never know how many defects you have. For example, if you kick out of this position one carbon atom, then this carbon atom moves, for example, to another position, typically interstitial. So the spectrum that you are going to generate is the spectrum with 2 defects, the vacancy and the interstitial. And this, from the experimental point of view, it's very difficult to recognize that this peak is generated by the vacancy and this by the interstitial. Whereas with the simulation, you can do the 2 models and separate them. Okay, just 2 more slides. You know, consider again our unit cell with 80 atoms that contains magnesium, and then we want to know if magnesium is contributing to one or more modes that are, you know, the horizontal axis represents the frequency. And look here, you see that the large, you know, the y-axis, the vertical axis, gives the shift that we obtain in the frequency when magnesium 24 is substituted with magnesium 26. And you see that we have an important shift only for the modes that are between 100 and 350 centimeters to the -1. All other modes are not shifted. They are shifted by 1-2 centimeters to the -1. So we can say that magnesium is contributing only to the modes at very low frequency. If we repeat the same for aluminum, we see that aluminum is in the intermediate zone, or silicon, and we can do this analysis. Okay, I think I'm running out of my time, so I think I can stop here, because obviously we could go on for 2 more hours, but I think it's enough.
Okay, thank you very much, Professor Dovesi, about this talk. Now we are open to the questions from the audience. We don't have questions. Okay, I have some questions about, because in this workshop we have many students in different stages. We have undergraduation, we have graduation. So I want to ask you about if you can tell some words about how it's so important to study vibrational spectroscopy and use gamma infrared, for example, to characterize materials in material science. So why it's so important in this kind of studies? You can tell about this.
Obviously, consider, for example, diamond. Okay, we know that diamond is done by carbon atoms, and we also know that it's impossible to have a very pure diamond. For example, diamond contains always fractions of other elements, and it contains intrinsic and extrinsic defects. But very often they are in a very low concentration. So you cannot, for example, know how many vacancies you have simply from the weight of your diamond, because sure. But if we are lucky, some of the defects generate a very peculiar peak, because suppose, for example, that in diamond, if there is a particular combination of defects, you can have that in carbon can have single bonds or double bonds or triple bonds, if you have some organic chemistry. So, for example, if you have a double bond around the defect, this is a very characteristic peak. You recognize very easily. Or if you have, say, 2 nitrogen atoms, this is again a very characteristic peak. So, and we can continue. Just giving some example. So the spectra, infrared or also EPR, electromagnetic resonance, can provide information. To do EPR, you must have uncoupled electrons. You know that the bonds in diamond are such that you have what is called a closed shell. You don't have uncoupled electrons. But if you cut, for example, when you create a vacancy, the 4 atoms around the vacancy are bearing an electron that is unpaired. And those 4 electrons can be all up, 3 up, 1 down, 2 up and 2 down. And so you can have 3 different spin states: quintuplet, triplet, singlet. And they have a different EPR spectrum, and they have obviously different energy. And then if you are lucky, and if you have a good sample, and if you are a good experimentalist, you can collect information from different spectroscopies and try to understand what is the microscopic structure of your object. Because the real point is that we don't know what is the microscopic structure of an object. We don't have, you know, a microscope that permits us to see if a bond is broken or not, or if there is a vacancy or two vacancy or a cluster of other atoms inside our system.
Okay. I have another question about the simulation of infrared spectra, no? Mainly in the part of reflectivity, no? You know that when you are working with materials, crystalline materials with disorder, no? Mainly the damping, no? The damping is very large. So the problem is we don't have in this situation a good compatibility between the experimental data and the simulated data from crystal. No, this occurs mainly because the damping crystal is artificial outputted. No, is about 8 centimeters to -1. No, there is a you think about how crystal can simulate the damping effect in crystalline materials.
You know, if I understand the question, I am not sure I catch exactly the question, but obviously there are two aspects. If we are discussing of perfect crystalline materials, things are relatively simple. And we could hope, you know, that there are attempts to go beyond the harmonic approximation, and also in crystal we started to implement something that is not yet standard, because if you know the anharmonicity, you can also try to compute the lifetime of the excited state.
The lifetime, the phono lifetime.
Yeah, and then the weight at the alpha maximum of the curve. But this is, you know, is still in progress. So, but I would say that the interpretation of the spectra of very well prepared crystalline compounds is very satisfactory. But obviously, when the crystallinity is not good enough, when the number of defects is important, or when the system has a relatively large amount of disorder, then the situation becomes more difficult, and I don't have really experience on how to simulate them. So from my point of view, obviously I'm always looking for good good spectra. I can give you an example.
Yeah.
In 2013, I was in sabbatic for 3 months in Nancy, and I worked with a very good experimental group in Raman. But then the problem was to have good crystalline systems, and actually we got from Japan a set of crystals sufficiently big to perform accurate Raman spectra, and they were so kind to send us the sample, because otherwise, you know, all the problems related to the defects, the not complete crystallinity, creates a set of problems that makes the comparison difficult.
Okay, thank you very much. I think we don't have more questions. Thank you very much, Professor Dovesi, for your last talk. So in this time we should continue to another talk, but the next one was cancelled because personal problem of the speakers. So now it's with Rodrigo or João can help me about the next step.
Thank you very much. Bye.
Thank you very much.
Thank you very much, Professor Dovesi.
Thank you.
And then I think it's good to close the session, have a large break now, and then continues after lunch at 2 o'clock.
Okay, I just have an announcement to make for all participants. I need to close the room, okay, and then I can open the afternoon section with the new panelists. So in order to invite the new panelists, I need to close this room and open the section for the afternoon. But the access link for the participants is the same one that I sent before. So if you receive the access link or if you're using the Eventbrite platform, you're going to be able to access the room with that same link. Okay, so thank you so much for the presentations of this morning, and see you there after lunch. Thank you.